Welcome back to my LGP21. This is my transistorized computer from 1963. That means that this year it's 63 years old, making it one of the oldest digital computers in the country. Although ironically, it's not the oldest digital computer in this room. That title's held by the Binix G15, but I think that this LGP21 actually looks better. It has that perfect mid-century modern aesthetic, and I just think it's absolutely beautiful. This particular machine started life at the Los Alamos Scientific Laboratories in New Mexico, changed hands once, maybe twice, before it ended up in the hands of Tom Jennings, the very same Tom Jennings that created FidoNet. And Tom really wanted to see this thing come up and work, so he reached out to me, and I drove out to California, had an absolute blast hanging out with Tom, loaded it up, brought it all the way back down here, and in the previous episodes, we've gotten this thing doing some pretty exciting stuff. We've had the CPU fully powered up and the absolute bonkers rotating disk memory spinning. We had the typewriter doing typewriter-y things, and we even got the CRT fully powered up, and we're able to see the contents of the program counter, the instruction register, and the accumulator. And we even saw that there was still code hanging out on this rotating disk memory after 40 years, maybe more. So what I want to do today is I want to dump the entire contents of this rotating disk memory, so that way we have it backed up and saved, and then we can start loading in new programs and doing more exciting things from there. But in order to dump the contents of the memory, we have to write a program and load it into memory. Thankfully, for whatever reason, we saw that track 0 and track 1 were completely empty. They were all zeros. That means that we can write a program, load it into track 0, execute it without having to worry about potentially wiping out any memory that's already on the disk. Although I'm getting very far ahead of myself here because we have an incredibly long road to travel before we can get to the point of loading a program into memory and executing it from there. But in that vein, there's been some incredible work going on over on the Discord. Paul, who made the G15 emulator that's on the internet, is working on an LGP21 emulator, and it looks fantastic. Bill, who wrote Doom for the G15, has been working very closely with Paul, so I'm convinced that that emulator is going to be amazing. Reese, who's the star of today's show, has actually written me a 3-page list here of how to go about testing initial functionality on the machine. This is essentially where we're going to start. This is really exciting. Before we do anything else, the first thing I want to do is get that motor start relay to stop clattering like crazy. So I'm going to pull the clamshell off and then remove the memory control board here. And that gives us pretty good access to the relay. Now there is a relay adjustment procedure here in my maintenance and training manual. So if I crack this open, and I've got it bookmarked here. There's a nice little diagram here showing what the adjustments should be to the motor start relay. And if these are out of whack, maybe that's why we're clattering like crazy. So I'm gonna pull out a feeler gauge and see just how close to these measurements we actually are. Getting access to the relay ain't easy with the memory disk in place, but I'm definitely not going to remove the memory disk again. So I'll just have to do my best contortionist act. Right off the bat, I can tell the first 2 clearances I measured are way out. Doing all the adding up and writing everything down, it looks like 3 of the 4 measurements are very much so out of spec. I'll slightly bend a few tabs to better adjust things and get them closer, but I'm skeptical if this is the actual problem here. One last thing I will do though is burnish the contact a bit. All right, I think it's better adjusted, but I got a feeling it's still gonna clatter, but let's power it up and find out. I'll flip the breaker on, then we'll hit the power switch up here. Yeah, I feel like it clattered worse actually. That's not good. But the disk is spinning, so now that the disk is up to speed, oh look at that, my stoplight works now. Well, waste not, want not, the thing's powered up. Let's try to do some stuff here. So I'm gonna flip it over to manual input and we get our IO light on. That's expected here. So I need to type, let's just type all zeros. And yeah, whenever I type, you can see that it shows up in the accumulator. So if I type all zeros here, it clears out the accumulator. How awesome is that? If I type like just random numbers and letters here, you can see it just fills the accumulator with whatever I'm typing. So let's fill the accumulator with instruction, and that instruction is going to be 000P 0200. So now we hit the fill clear button. So if I do that, yeah, it cleared the program counter to 0, copied the accumulator into the instruction register. That's exactly what's supposed to happen. A whole lot of this thing is working like it's supposed to. Okay, so we're gonna do a 4, 8, and then 1, 2, 3, 4, 5, 6 zeros. So I'm gonna pull it out of manual input into one operation. I'll go ahead and put a carriage return on this thing. Now, if I hit execute, it should print the number 4 on the paper, and that's it. So here we go. So it printed the number 4, but it never stopped printing the number 4. What's up with that? Let's try it again. Let's do it one more time. Something is not right, but that's pretty cool. So I went through and I just kept hitting execute over and over and over again, and we always got a varying number of 4s. We should only ever get 1 4, but we were always getting a bunch. So that's a problem, but I thought I would try a different character, and this has now highlighted a new problem. So right now you can see that we have random stuff in our accumulator and our instruction register, because I've been playing with it here. So if I do 0, 0, 0, well, you can see it right there. As I'm loading something into the accumulator, it's affecting the instruction register up there, and it absolutely should not be. So then if I do a P0200, that is the instruction that we've been running, which is print a single character. If I do a fill clear now, we can see that it copies that over to the instruction register. Now, if I try to fill this with all 5s, oh, this time it's gonna work. Of course it is. All right. Geez, I have no idea what's going on here, but pull it out of manual input into one operation, and then I'll just go ahead and hit execute, and it should print D this time. And it did, and it hasn't stopped printing D. There it goes. Oh, that's a lot of Ds. But if I go ahead and toss this back into manual input, I want to see if we can get the accumulator to affect the instruction register again here. Man, yeah, it really doesn't seem to be doing that now. All right, let's hit a fill clear and just move some stuff over here. There it goes. You guys saw how it's changing there. Look at that. That I'm like 90% certain should not happen. All right, we got problems, but don't let this distract you from the fact that Hector's going to be running 3 Honda Civics with spoon engines.
Come on, man, white boys work fast, don't they?
And also don't let this distract you from the fact that we just typed an instruction on the Flexowriter that loaded into the accumulator, then we transferred the accumulator into the instruction register, and then mostly successfully executed that instruction. The amount of things that have to go right for that sequence of events to happen is insane. Most of the machine is very healthy, but like I said, we got some problems. The first is that the motor start relay still clatters, and I'm pretty sure I made it worse by trying to adjust it, so hooray for that. Also, as you saw at the end there, sometimes whenever we're inputting a value into the accumulator, it influences the instruction register, and that absolutely shouldn't be happening. So that's going to be deep inside the CPU somewhere. That one's going to be a real proper bear to figure out. So what we're going to do is we're going to ignore it for now, and we're going to focus on the problems in the Flexowriter. That instruction that we loaded should print a single character and then stop. And we were seeing that it was printing anywhere from 4 to 40 characters. So if we look at my little manual here on this page 5-3, this is the Flexowriter print routine, and there's a big long explanation about it. But if we go to the next page, it's got a nice little block diagram of what happens whenever the FlexTally IO board tells the Flexowriter to print a value. And we can see that there's kind of a lot of stuff going on here, but the 3 things that intrigue me the absolute most about this diagram are right here on the bottom, and that's STC1, STC3, and STC4. And that's because they have these little numbers and arrows next to them. And you can see that STC1 has an arrow out at 20 degrees and an arrow in at 320 degrees. STC3 is 260, 300, STC4 is 250 and 310. This tells me that there's some kind of cam inside of the Flexowriter that is making and breaking contacts at very specific rotational points. So if we flip all the way over to the back here where the Freedom Flexowriter schematic is, we can see that on my version of the schematic at least, somebody's already gone through and circled STC1, STC2, STC3, STC4, and looks like SC7. This is a little bit of an indication of things to come here. So STC3 here, you can see is 260 degrees and 300 degrees it goes out. And we can see the line from that is reset for storage clutch drivers, and it's on pin JL29. So let's pull on this thread a little bit here and come over here to the Flex Tally schematic, and we can see that there's a whole lot more notes on this one, handwritten notes that I didn't write. You can see right up here on the top it says translator driver reset from Flexo, stop code. I think we're not the first people to try and troubleshoot this problem on that Flexowriter. I think this has been a problem probably for years, and somebody dove into it and didn't successfully fix it. And you can see that JL29 is a common input to these collections of, looks like flip-flops with a driver on it that go to TP1, 2, 3, 4, 5, 6, and TX. This is kind of a strange way to lay it out. So if we circle back over here to the logic portion of the manual here, and it is what they call a bistable device. So essentially it's a flip-flop with a power transistor on the outside. But the reason that I brought us over to this page is because we can see that somebody has also drawn a little arrow down here that says JL29. So again, we're in the exact same place that somebody was previously. But this page, it kind of explains exactly how that works. But I think what's actually going on here is whenever the CPU wants to send a character to the Flexowriter, it internally translates that character to 6 bits and then latches those 6 bits into these flip-flop drivers here and try to transmit this value out continually until it receives a reset pulse from the Flexowriter down JL29. Now, if that reset pulse is not hitting correctly or hitting inconsistently, it'll just print the same character over and over and over again, which is what we're seeing. So I think we need to take that Flexowriter apart enough to find the cam for STC3 and see if we can clean the contacts on it at the very least. That might help clear it up. Just a reminder, the manual says this Freedom Flexowriter weighs in at 85 pounds. That's something like 26 rabbits. The cam that we need to get to though is hidden in this part underneath the keyboard called the code translator. To get that out, I need to remove one of the rubber feet, pull off the tape reader cover, then undo 4 mounting screws that are arranged around the periphery. You can actually see the whole code translator shift loose when I loosen this last screw. Then you have to rotate it slightly and the whole thing pulls free, kind of. There is a massive bundle of wires that you can't unplug, so I need to set the typewriter back down with one hand while carefully holding the code translator with the other. This was a bad idea. My back immediately protested very loudly. At any rate, the last step is to remove the 2 screws holding the dust shield in place. While getting this out, I only slightly hurt my back a lot, but I'm popping ibuprofen like they're Skittles, so we're good. But this is fascinating. Not only does this machine have an oil level, it has a camshaft and Zerk fittings. It's like working on a car here, but the contacts that we're concerned about are right along here because those are the contacts that are riding on the camshaft. These 4 groups of contacts right here have little plastic arms that connect them up to essentially roller rockers that are riding on the camshaft. And as that camshaft turns around, these are going to make and break at specific rotational positions. And so I'll give it a little bit of a rotate here, and you can see that they are indeed making or breaking contact. Now, I don't think anybody has ever cleaned any of these contacts. I don't think anybody's been in here since this thing was built 60 years ago. So I think what we need to do is go through and clean all of the contacts on these. This is STC 1, 2, 3, and 4. 3 in particular is the one that we're concerned about because that's the one that has to deal with sending the reset code. So I need to go through and burnish all the contacts on these switches, just like trying to repair an old pinball machine. Then, while I've got good access to everything, I'll pull the oiler out and get oil onto anything that turns, slides, or moves. I'll rotate the thing by hand as well, making sure that the oil works its way into all the nooks and crannies and liquefies the existing grease, turning it back into grease instead of glue. And it's actually a really good thing I did this, because there are 4 roller rockers that ride on the camshaft lobes, and 3 of the 4 were completely seized solid. You can just see in this shot that only one of these is rotating. I spent the next 2 hours slowly working the roller rockers back and forth, getting oil to seep into them and break them loose. But it paid off, because check it out, everything is moving nice and smooth for the first time in probably 30 years. I was chatting with Roy over on the Discord, and he figured out that our problem with the accumulator affecting the instruction register might be due to a bad fill clear switch here. You can hear that if I press execute, it's got a really nice click to it, but fill clear doesn't. And these are supposed to be the same type of switch. So I'm gonna drip some deoxit into here and actuate it about 1,000 times, and hopefully it starts making better connection, and that solves that problem. All right, let's see if I made everything exponentially worse. Let's go over to manual input here. The IO light comes on, and then we want to do 0, 0, 0, P, 0200. And it looks like we filled our accumulator correctly with that, so I'm gonna hit the fill clear button here. That cleared the program counter and moved it up into the instruction register. Now let's just type a bunch of 5s here and see if it influences the instruction register. Oh, it does. All right, man. Okay, so let's just try it again. Maybe that button is still giving us problems. So 000P0200, fill clear. And I'm gonna hit the fill clear button a couple of times here. Maybe we can get proper connection out of it. And then let's go with a 5. Yep, now it's working fine. Okay, 5, 5, 5, 5. We'll just fill the accumulator with 5s. We'll pull it out of manual input into one operation. We'll hit execute, and we want 1 letter D. Yes! We got 1 letter D! Oh, thank you. All right, so it works. It works. All right, now we can start running more complex stuff. This is awesome. So we can type an instruction into the accumulator, move it into the instruction register, and execute it successfully with the correct response being printed out on the typewriter. That is amazing, but also means that we can now bootstrap the system to run more complex software. But in order to run that more complex software, we have to have some way to load it into the system. Now, I could use the paper tape reader on the Flexowriter, except that it's not working correctly. If you run it without a paper tape installed in it, it just prints out the letter M, which is the incorrect letter for all 6 bits being set. So, man, I really don't want to take the Flexowriter apart again, but also, ultimately, I don't want to use that paper tape reader anyways, because we have this beautiful thing hanging out here, the Tally high-speed paper tape reader meant to be used with this system. And actually, I think this thing is pretty simple. The paper tape reader mechanism up here is just a bunch of star wheels that push on contacts. And the schematic for the internal electronics is dead simple. There's just a couple of lights, a couple of diodes, and a few capacitors, and that's it. So I am slightly worried about some of those caps, so we are gonna pull it apart, try to take a look at those caps and see what's going on inside of there, clean everything up, lube anything that needs lubing, and then plug it in and try to read a paper tape with it. Thankfully, compared to the Flexowriter, the tape reader is super lightweight, and I'm not the first person into this thing either. There's supposed to be 8 screws holding the back panel on, but there's only 3 installed. And with the panel removed, that's gross. Time to get the vacuum cleaner out and evict all the dead spiders. The tape reader itself is actually bolted to the frame with 4 screws through the front, kind of like a rack mount thing. It's super easy to pull out. Then I can carry it out to the air compressor and blow off the decades of dust. Once the bulky stuff is off, I'll pull out a paintbrush and use that to get the more stubborn stuff clean. The rubber belt for the motor and the rubber bands for the take-up wheels are not great. They have pretty brutal memory and are pretty stretched out. I'll boil them in water to try to revive them as best as I can, and the drive belt looks like it'll be fine, but the take-up wheel rubber bands are likely going to need to be replaced. This thing has like 5 differentials in it, and they were all seized in place. I went through and oiled absolutely everything, and then slowly worked each shaft back and forth, working the oil in until things started to free up. While I let the oil seep into the tighter nooks and crannies, I need to get the drive motor out of the way so I can get access to these 2 screw heads that were underneath the motor. And these are the mounts for a large AC motor run capacitor that is underneath the base. I've had terrible luck with AC capacitors in the past, and I just so happen to have a spare in the right capacitance on hand. So I'll go ahead and remove this one, then solder in the new one, which is the same thickness and shape, but about half the length of the original. All right, this thing is super cool. It's starting to loosen up a little bit, and I mean, there's all sorts of wild gearboxes going on in here because the electric motor only rotates in one direction, but we need to be able to go forwards or backwards. So they've got this wild gearbox going on. Essentially, you have 2 solenoids, one right here and another one over here, and they clip into these little teeth that stick out here and prevent one side or the other from rotating. So if this solenoid pulls, we can go this direction, which causes the center shaft here to rotate clockwise from the orientation that I am. But if we latch that one and open up the other one here, now that center shaft is rotating counterclockwise while the motor is still rotating in the exact same direction. How cool is that? On the front side here, the reader is hidden behind this little plate right here, and it's so simple. I absolutely love it. There's these little star wheels right along here that can fall into or be pushed up by holes in the paper or a lack of holes. And if those are pushed up, they push on a little spring that makes or breaks a contact, and that's it. I love this design. It's so simple. It's just really cool. All right, I need to get some power into this thing, but there's not really an easy way to do that because the cable is not a normal cable. So I'm just gonna use the computer to do it. I don't have the CRT plugged in right now, but that shouldn't make any difference here. All I'm gonna do is hit power here. I'm not even gonna turn the Flexowriter on. The tape reader itself has a separate power switch on it. I have no idea what the state of that is. So when I flip the power on here on, it may automatically turn that one on as well. Now these take-up wheel rubber bands are not great, but that's not a big deal. As long as we can move the tape backwards and forwards, we can read in a program, and I'll try to source new rubber bands for this at some point in time. The primary drive belt does look okay though, so fingers crossed it all goes okay. So let's flip the power on here. Oh, let's turn that one off. Okay. Whew. That power switch was on, but I'm not gonna mess with that until I know that this thing is up and stable-ish. All right, we did see it spin briefly there as it powered up with the power switch on, but we're gonna try and get it spinning for a little while and let the grease kind of liquefy a little bit, and I'm gonna oil it up as it does this. So let's flip the power switch on here. Yeah, there it goes. Yeah, I'm just gonna drip a little bit of oil right in here on these moving parts. I know there's oilers here as well, but those are already full, so I'm just trying to get it to wick in from the sides as well. All right, let's see if we can get it to go in a direction. I'm gonna go ahead and flip it into forwards here. Excellent, did not work. Okay. All right. All right. Oh, there it goes. All right. We were just kind of a little stuck. All right. The paper tape reader is starting to loosen up, so I think we're ready to load in a program. If it looks weird that I've got like multiple microphones and headphones on, it's because I'm on live with the Discord. So everybody on the Discord say hi.
Hello.
Hi.
Hello.
Hi.
There we go.
Hi.
Reese is gonna walk me through what we need to do here, but there is a slight caveat in that I think we've discovered that track 0 and track 1 are bad. I don't think they're bad on the disc. I think we have maybe a bad diode or a bad transistor on those tracks. And so what we're going to do is we're going to load the program into track 2 and execute it from there so that we can dump the entire contents of the disk. And we've backed up track 2 manually by looking at the CRT over here. So we're not going to blast anything super important here, I don't think. All right, so we've got to type a little bootstrap to get it to start reading from the paper tape reader over there. So Reese, if you can read out the bootstrap for me.
Okay. 000C02QJ.
That's going to be a fill clear.
800I.
Okay.
0000.
And then that is a one-op execute, right?
Yes.
Okay.
And now switch to normal and start.
Oh, there it goes.
Hey!
Oh, that's mental. Check it out. This thing is reading. Almost done reading. Oh, Jesus. Oh, man.
Well, it starts with track 1, so that's what we expect. But when it gets to track 2, we should start seeing data.
All right, so what Reese's program is doing here is it's going through and reading each word from every single track and printing it out on the typewriter here. This seems like a very strange way to back up all of the data in memory, but it was actually the most dense way that we could think of. If we were to try and punch the data out on like paper tape, it would end up taking like 300 feet of paper tape. But this way we can do it in about 10 pages, and then I'll scan those pages and we can OCR them, and then we have a full backup of everything that was on the disk. This is pretty exciting. So I'm just gonna sit back and let it slowly make me deaf. This CRT diagnostic panel is the greatest thing ever put on a computer ever. I mean, just look at it. It's gorgeous. But also, let's break down what we're seeing here. The bottommost trace shows the accumulator, the middle trace shows the instruction, and the top trace shows the program counter. We loaded our program into track 2, and you can see that the program counter is always in track 2, jumping around to a bunch of different sectors within that track. Below that, the various instructions from those sectors in track 2 are getting loaded up and executed one by one. But the real party piece here is the accumulator on the bottom. You can see it load a value from memory into the accumulator, then it shifts that value out 4 bits at a time over to the typewriter. We can literally see it pushing data out the left side of the accumulator over to the typewriter to be punched out on a piece of paper. It's just so mesmerizing to watch, without a doubt, my favorite part of this machine. A little over an hour and a half later, and check it out, 9 pages of the entirety of that rotating disk memory. How awesome is that? It is backed up, it is safe, and every single track had something in it, except for track 0, 1, and 2Q and 2W. Those came back as all zeros, but likely there's actually data on there, and we have some kind of hardware fault that's not reading those tracks correctly. So that's something that we're gonna need to troubleshoot in the next episode, but the Flexowriter performed admirably. Also, our fill clear button seems to be working totally fine now. After letting it soak with deoxit in it overnight, it now makes a nice clicky sound. So I think that thing is working as well. The CRT was flawless the entire time. The paper tape reader is mostly working. It's starting to loosen up enough that whenever the computer sends it a signal to read forwards, it does initiate that and let that go. But it's having trouble getting into reverse. Things are still just a little too sticky. So I think the more that we use that, the more that we let it run, the more it's gonna free up and loosen up, and the more normal it's gonna become. After that, the only thing left is the punch, and that's kind of low priority. We're not going to get into that until after VCF Southwest. So this thing is coming together unbelievably well. I am beyond excited. It ran for over 2 hours today. The computer is, I mean, like 85 to 90% of the thing has to be working perfectly in order for it to have run this routine and dumped all of the memory. Pretty much the only thing that we haven't tested is like multiplication and division. So just absolutely incredible. Massive shout out to Reese. Thank you so much for helping us get this to happen and getting the software for it. Huge shout out to Roy for walking through the hardware with me and helping me understand exactly what's going on. Massive shout outs to Bill and Paul for the work on the emulators. This is an amazing project. So I want to thank you all so much for hanging out with me today, and I hope to see you in the next one.